Yeah, in this video, I'm going to discuss about this VSEPR theory or this valence shell electron pair repulsion theory. This is from the degree first semester syllabus, that is 10th chapter, chemical bonding. In my previous videos, have dealt with this Lewis theory and Sedgwick bubble theory and the limitations. Now, let's deal with this VSEPR theory, which is very important and the easy topic too. So the rest of the chapter has been uploaded on my YouTube channel. If you can go through it, and if you like it, please like, share, and subscribe my channel. Yes, let's look at these postulates of this VSEPR theory in detail one by one. Yeah, before this, the because of the limitations to the Lewis theory, the various theories have been put forward later. The rest of this, the main was the Sedgwick-Powell theory, which says that uh, Sedgwick-Powell theory, which says that the shape of the molecules can be predicted or can be known depending upon the number of the valence electrons. That means both lone pairs and bond pairs of electrons. So both lone pairs and bond pairs of electrons in this theory were considered to be equivalent. But this has been improvised to a certain extent because it could not give the shape of the molecules and bond angles perfectly. So this later, in 1957, this Gillespie Nilom improved this theory and gave a better theory, which is nothing but the valence shell electron pair repulsion theory, that is VSEPR theory. Again, yeah, the name seems to be little big, but this is very easy. This name itself suggests what is there in this theory here, or it is sometimes it's also called as VSEPR theory. So your wish, you can call it as you like, as VSEPR theory or VSEPR theory, whatever. So all this theory is all about the presence of or the valence electrons which are present in an atom. So this theory is based on the valence electrons which are present in an atom. So when we go to this is VSEPR short form. So this is valence shells. So we know that there's a nucleus in the center of an atom, and there is shells around this which are filled with electrons, right? So the shells. So now this theory is all about the electrons which are present in the outermost shell here. So we know that the electrons which are present in the outermost shell are valence electrons, and these are the electrons which are participating in the bonding or which are influencing the structure of an atom, or which influencing the bonding with the other atoms. So it is these electrons which are playing an important role in the bonding, in the chemical bonding. So we concentrate on these electrons now. So valence shell electron pairs. So when we come to the valence electrons, or these electrons which are present in the outermost shell, these can be lone pairs or bond pairs. So these electrons can be lone pair of electrons or bond pair of electrons. So what do you mean by this lone pairs and bond pairs? I've already dealt with this in my previous video when I'm doing this Sedgwick-Powell theory. But once again, for your review, if you've not seen that video, I'll tell you this bond pairs are nothing but, if you take an example of, suppose I'm taking simply this ammonia, right? Ammonia, this we know that nitrogen is electronic configuration is 2 and 5. So outermost is 5 electrons. That means it has 5 electrons in the valence shell or in the outermost shell. So 3 are involved in the bonding, and one of this is a lone pair which is present on this. So when I say this is bond pair and this is lone pair, what does this mean? So this bond pair is nothing but the electrons which are involved in the bonding with the other atoms. So the nitrogen, it has if it has 5 electrons, 3 of these electrons are involved in the bonding with this hydrogen, right? So this electrons which are involved in bonding with the hydrogen are nothing but the bond pair of electrons here. so which are involved in the bonding. There's a tightly held in between these two hydrogens, and they cannot move now. They're particularly they are in a certain space. They have certain space which is limited to them there, and they can't move from there. So we can say them as uh, rigid, or they cannot move. Right. Now, when we come to this lone pair of electrons, these lone pair of electrons are not bonded to any of the other atoms. They're simply there on this only one atom, though the lone pair of electrons in this particular case is under the influence of only this nitrogen now. So so the lone pair of electrons means they're lonely, they're not bonded, they're under the influence of only this nitrogen atom, and they have all the space for themselves uh, around this nitrogen atom. So we can say this lone pairs as they occupy more space, or they're not localized. In other words, they're delocalized, they're free to move. Then when compared to that of this uh, bond pairs, they occupy more space. In other words, they're occupying more space, these lone pairs. They're free to move around this nitrogen atom, this central atom. So this nitrogen is a central atom here in that particular sense. I'll deal with this, what is a central atom, in my next slide. Okay, but so coming back, these bond pairs are those which are more uh, rigid. I mean, they fix to a particular space or place around this nitrogen, and these lone pairs, as are bonded to only one atom, they are under the influence of only the central atom. They are free to move there, and they occupy more space around this nitrogen. So this is the difference in between the lone pair of electrons and bond pair of electrons. So what this theory says is all is that the theory is based, that means it gives the shapes of the molecules uh, based on these valence electrons, and we know these electrons are under repulsion. So the electrons are they're negatively charged, they repel each other. So based on these repulsions in between these electrons, whether they are lone pair of electrons or bond pair of electrons, the shapes of the molecules is decided. So this theory is all about the presence of the repulsions in between the electrons which are present in the valence shell. So the theory is based on the repulsions. I repeat it, it's very important. So the theory is based on the repulsions in between these valence electrons of an atom, right? So next postulate where we'll come to this. So so now it's better I take an example of water molecule here. So this water molecule, I'm sorry, this is hydrogen, right? Sorry. Yeah. The central atom is oxygen here. So H2O, and it is held to two hydrogens by means of two bond pairs, and there are two lone pairs which are present on this central atom now. So this oxygen is 2 and 6. There are 6 valence electrons. So two of them are held to two hydrogens, and that means they are held by means of two bonds, and it has two lone pairs of electrons. So on this central atom. So we know that now we've come to the conclusion that the theory is all based on the repulsion in between these electrons now. So So, yeah, and repulsions in between these lone pairs and bond pairs of electrons. So, as these lone pairs of electrons which are present on the oxygen are occupying more space, as I said this, so they are held only to this oxygen atom. Their influence on they're under the influence of only this oxygen atom now. They try to occupy more space around this central atom. So there will be repulsion in between these lone pairs of electrons. I agree that there is a repulsion in between these bond pairs of electrons also, but the lone pair repulsions, I write it here, lone pair repulsions are more than bond pair repulsions, and which is further more than bond pair repulsions. just just don't muck up this as it is, just try to understand the logic behind it. So I'll tell you again. So this lone pairs which are present is under the influence of only one atom. They are loosely held. They can occupy more space around this central atom, so they try to repel each other. So the repulsion is more in the case of the lone pairs. And when we come to this lone pair bond pair repulsions, this is little less than this lone pair, because this bond pair is held, it's rigid. This rigid in between these two atoms. It is not free to move around the central atom. They're occupying little space around this central atom. So the lone pair repulsions is more than lone pair bond pair, and which is more than bond pair. So when we come to these two bonds here, the space in between these two, yeah, the repulsion, I mean the repulsion in between these two electrons is little less when compared to that of this lone pair bond pair repulsions. So this is the logic behind why this lone pair repulsions is more than lone pair bond pair repulsions, which is more than bond pair repulsions. So if you understand this little logic here, we can proceed a little further. So so the shapes of it is totally based on the repulsions in between these lone pairs and bond pairs, or whatever, bond pair and lone pair bond pair repulsions. Yeah. So um, so in other words, I can say that the lone pairs and bond pairs will try to arrange themselves around this central atom in such a way that they are at a distance so that there is a minimum repulsion. So we can write this as they are at the maximum distance. So yeah, distance between them is maximized and the repulsion between them is minimized. So they are at the maximum distance so that the repulsion is minimized, so that the minimum they can face this minimum repulsion. So this is the main postulate of this theory, where we can say that the atoms will tend to arrange themselves in a manner that there is a minimum repulsion in between the electrons and the distance between them is maximum. So this is the main postulate of this VSEPR theory. Yes, and because of these repulsions, we can say that, I'll draw this once again here. You can understand. So these two lone pairs of electrons which are present here, because of these repulsions here, uh, there is a distortion in the shape of the molecule. The normal shape of the molecule will get distorted, or the geometry is distorted in the shape of the molecules. I'll write it here, because of the repulsions in between the electrons, because of repulsion in between the electrons, right? So this is the main thing. If you understand this, the rest of the part is very easy. So because of these repulsions in between these two between these electrons which are present in the valence shell of these atoms, there is a distortion in the shape of the molecule. Yes. When we come to the next point, the main postulate is, we can say that the magnitude of the repulsions in between these bond pairs of electrons depends on the electronegativity difference in between the central atom and the other atoms. So for example, when we take this ammonia and yeah, NF3, so if you, the electronegativity difference in between nitrogen, here nitrogen is more electronegative than hydrogen. Here fluorine is more negative, electronegative when compared to that of the nitrogen. Because so So the repulsion in between the electrons in these two cases will depend upon the electronegativity difference in between these two atoms here, central atom and the other atoms. Based on the electronegativity difference, we can arrive at the shape of the molecule where the repulsions in between the electrons will also differ. We'll discuss uh, about this in the later part of the video. Shape of the molecules will differ because of the difference in the electronegativity difference in between the central atom and the other atoms, because of the difference in the magnitude of the repulsions. Yes, just yeah. And the other postulate and the main postulate of this theory is all bonds are treated as single bonds in this case. So when you take an example of carbon dioxide here, the shape of it is linear here. Even though this is a double bond, this oxygen, okay? There's a double bond in between this carbon and oxygen. They are treated as single bonds here in order to arrive at the shape of the molecules here. So when we come to this BeCl2, the shape of this also is linear, and the shape of this O2 is also linear, where we consider this double bonds as a triple bonds here, and multiple bonds, any bonds. For this case, the triple bond is also considered as a single bond in this case, according to this VSEPR theory. Yes. So this is the main postulate of this theory. So according to this VSEPR theory, till now we have come to the conclusion that the VSEPR theory is all based on the presence of the valence electrons in the outermost shell of an atom, and there is a repulsion in between the pairs of electrons which are present in this central atom, that is the lone pairs or the bond pairs, and depending upon the repulsions in between these pairs of electrons, the shape of the molecule is decided. Yeah, these are the main postulates. And now let's look at the shapes of the molecules, few molecules, depending upon the VSEPR theory. Till now, what we have learned, just try to apply them in arriving at the shapes of these molecules. So when we take this BeCl2, let's look at this small formula before going to the arriving at the shapes of molecules. This is uh, steric number, is not serial number, okay? So this is half of number of valence electrons. Oh my god, what happened? Yeah. So number of valence electrons plus number of atoms attached by means of single bond plus the negative charge if it has any, minus the positive charge if it has any. These are the charges, okay? If it is a negative charge, just add them, and if it is a positive charge, let's subtract them. Okay, so now for BeCl2, this Be is a hybrid, I mean the configuration is 1:2 to S2, that is outermost configuration is 2 electrons, it's valence electrons. So half into valence electrons is 2. So when you look at this, it has bonded to BeCl2, right? 2 atoms. That means number of atoms which are attached by means of single bond is 2, as there is no charge here. Just leave these 2, and this is 4 by 2, which is 2. If this number is 2, we can conclude that the shape of this molecule is linear here. So you can write it as the linear, where the bond angle here is 180 degrees. Linear here. So Now I like to give a basic difference. What is the geometry and what is the shape of the molecule right now? So if there are, I'll tell you one thing, no lone pairs, then the shape of the molecule is nothing but the geometry of the molecule here. But if there are lone pairs which are present on the central atom, then the shape is different from that of the geometry. So now in this case, as there are no lone pairs, just remember that this BeCl2, when the steric number is 2, it is linear in shape. When we come to the lone pairs, in my next example, I'll tell you how to deal with this. Yeah. Now, we're coming to this boron trifluoride. You remember the example, right? This boron is 2 and 3 configuration, that is 1s2, 2s2, and 2p1. The valence electrons which are present are half into 3 plus number of atoms which are bonded to it is 4. When we see that, so there are 3 valence electrons here. These 3 valence electrons are involving in bonding with these 3 fluorine atoms. So there are no, no lone pairs and no charges also. What is this? Half into 3 plus 3. Yeah. So which is nothing but 3 here. So if this number is 3 here, we can say this shape is trigonal planar. So what is the shape of the molecule? If you say this, see, they are arranged at the corners of an equilateral triangle here. So how did this look like? It is trigonal planar. Simply trigonal planar. Here is the geometry of the molecule. There are no lone pairs because all the 3 valence electrons are involved in the bonding with these 3 fluorine atoms. We know that there are no lone pairs. This shape is nothing but the geometry of the molecule, in this case of BF3, which is nothing but trigonal planar. Yes. Or simply plane triangle also, we can say this. Now coming to the next example, when we take this, yes, yeah, I'm taking an example of methane here. This carbon is again 1s2, 2s2 and 2p2, right? So carbon is 6. Carbon is 6. So electronic configuration is this thing. So 4 valence electrons. So half into the number of valence electrons is 4. Number of bonds, atoms which is bonded by means of single bond is 4. As there is no charge, it is 4 here. So this methane is arranged in the form of a regular tetrahedron here. So we can see this, right? So one bond here, and it's bonded in such a way that it's minimum repulsions. So it is, the angle is 109.28. So it's arranged in such a way that the repulsions in between these bonds is minimum here. The space of electrons, there is a minimum repulsion. So at an angle of 109.28, there is a minimum repulsion in between these bond pairs of electrons. So the shape here, we can say this is a tetrahedral, and as there is no lone pairs, the geometry is nothing but the shape of the molecule here. So, right. So, when we come to the next example, that's ammonia. Yeah, here stars. Okay, now this nitrogen is 5 atomic, 7, sorry. This is 7. So it is nothing but 1s2, 2s2 and 2p3. That means the total number of valence electrons is 5 here. So half into valence electrons plus the bonded atoms here 4 again. So according to this, the shape of the molecule will be, the geometry of the molecule will be tetrahedral. That means the arrangement will be like this, right? H, H, H. So we know that this out of these four, three are bond pairs and one is lone pair of electrons, right? So this lone pair of electrons here is spaced like this. If the molecule were to be tetrahedral in this case, experimentally, it has proved that the angles in between them is not 109.28, but it is something around 107. So what is the angle here? What is the bond angle here? It is something around 107.48. So what is happening in this is, I said you already, this the lone pair which is present on this nitrogen atom. It is under the influence of only this nitrogen atom, that is a single nitrogen atom. So they occupy the more space around this, though they try to repel these bond pairs of electrons. We know that this lone pair bond pair repulsions will be more than bond pair repulsions. So bond pair repulsions. Because of this lone pair bond pair repulsions, which are more in this case, they will try to occupy more space and try to repel this bond pair. As a result, these are brought little close to each other, these bond pairs of electrons. As a result, the angle is reduced from 109 to 109, 107.48 in this case. So now this is the geometry here. So what is the geometry of the molecule here? It is tetrahedral, but when we come to the shape of this, it has become, when we look at the shape of this, see here, these are the lone pair of electrons, this yellow one, how it is looking like this. This is like a pyramid, like so. This is pyramidal. So what is the shape of this ammonia now? It is pyramidal because of the repulsions in between this lone pair and bond pair repulsion. So this, when you observe this theory is based purely on the repulsions in between the valence electrons. So the name valence shell electron pair repulsion theory here. So this is the difference in between the geometry and the shapes of the molecules. Whenever we are taking the geometry of the molecule, both lone pairs and bond pairs are considered. But when we are taking the shape of the molecule, only the bond pairs, or that means only the atoms which are surrounding the central atom are taken into the account and not the lone pairs. So ignore these lone pairs while taking the shape of the molecule. So how does this look like when we ignore these lone pairs? It's just pyramidal in shape. So the shape is pyramidal. So when there is one lone pair present, the shape is not tetrahedral. The geometry is tetrahedral and the shape is pyramidal in shape. So this is what about ammonia. And let's look at this water molecule shape also based on this VSEPR theory. Yes. When we come to this water molecule here, again, this oxygen here, it is 6 valence electrons, yes. So 1 is 2, 2 is 2, and 2p4, right? So number of valence electrons is 6 here. So half into, when you come to the steric number here, so 6, the number of atoms which is bonded to is only 2 here. So it is half into 8, which is nothing but 4 here. So according to this VSEPR theory, the fourth postulate, what I said is the double bonds are treated as single bonds here. So this where the application of this VSEPR theory comes. So double bonds are treated as single bonds here. That is why even if this oxygen is double bond, we are taking it as a single bond in this case. So now this 4 This oxygen now needs to be tetrahedral. That means the geometry is no doubt it is tetrahedral, but when we come to the shape of it, so these are both lone pairs and bond pairs of electrons, right? So the bond pairs of electrons are 2, lone pairs are 2. So this oxygen now it is bonded to two hydrogens by means of two bond pairs and two lone pairs of electrons which are present on this oxygen atom. So we know that this lone pair repulsions are maximum because they occupy more space around the central atom, which is more than lone pair bond pair repulsions and which is further more than bond pair repulsions. So because of this repulsions or more, they try to repel farther apart, which will repel this, and which in turn this bond angle is reduced further to 104.27. So the bond angle from 109 is reduced to 104 here. So now if the steric number is 4 here with the presence of two lone pairs. The shape is now, the geometry is tetrahedral and the shape is angular or bent also we can see. See this. These are the two lone pairs. How does this look like? It's angular or bent or V shape also. So this is the shape of the water molecule according to the VSEPR theory, and it clearly says that the bond angle is reduced from 109 to 104.27. This is the main application of this VSEPR theory. Yeah. So now let's look at this PCl5, a little more complicated example. We have taken here this phosphorus is 15, right? So 1 is 2, 2s2, 2p6, 3s2, and 3p3, right? So 5 electrons in the valence shell. So half into 5 plus 5. So total number of atoms it is bonded to is 5. So it is 5. So we are arriving at the new steric number, that is 5. So this is 5 is bonded to 5 other chlorine atoms in this manner. So when we look at the shape of this, yeah, this is one plane of a molecule, and above and below the plane, there are two other chlorines which are bonded to this phosphorus. See, this is one plane of the molecule here, and above and below the plane, these two chlorines are connected here. So how does it look like? This bipyramidal, right? Like two pyramids, above one pyramid and below one pyramid. When we take this as a plane, this triangular structure, it is a pyramid above this triangle and pyramid below this triangle. So how do you name it? Depending upon the uh, figure there, it is trigonal because triangular structure, and two pyramids here, bipyramidal. So simple to name this, right? If you try to understand the pictures, it's very simple to name them. Don't mug up them, okay? It is trigonal bipyramidal. So now the geometry is nothing but the trigonal bipyramidal. And when we look at these angles here, so this is one plane of the molecule. So this is 120 degrees, and here it is 90 degrees. So here, when you see this, this is these three, and these three bonds are at an angle of 90 degrees. And when we look at this angle in between this bond and this, it is 90 degrees. See it's carefully. This is 90, right? So there are two angles we can observe here is 120 degrees and 90 degrees. And one more thing I want to specify here, these are called as, yeah, I'll draw this again here, P, Cl, Cl, Cl. So this is one plane of the molecule, right? And above the plane and below the plane, there are two other chlorines. Yeah. So these are called as equatorial bonds. These are called as axial bonds. Okay, so there are two types of bonds. These are shorter bonds and these are longer bonds. So the axial bonds are little longer when compared to that of this equatorial bonds. So yeah, this is important here in our next discussion to remember these are equatorial bonds and these are axial bonds, right? So the geometry is here trigonal bipyramidal and the angles are 120 and 90 degrees here. Yeah. Let's look at one more example when we come to this SF4 here. Yes. This sulfur here is 16 atomic number. So it is 2, 8 and 6. So outermost electronic configuration is 6 again. So half into 6 plus 4. That is number of atoms it is bonded to is 4. And 6 is the number of the valence electrons. So it is nothing but 5 here. Okay. So since it is 5, it is hybridization will be sp3d2. sp3d, sorry. Yes. In what previous case, in linear, I forgot to tell you that it is sp in case of linear, and trigonal planar, it is sp2, and in tetrahedron, it is sp3, and trigonal bipyramidal, it is sp3d. Yes. The hybridization is sp3d here. So since it is 5, so what we expect here, it is trigonal bipyramidal. But out of these 5, 4 are involved in bond pairs and 1 is lone pairs. So the question arises here, so where this lone pair has to be placed here. That is why I've discussed about this equatorial and equatorial bonds and axial bonds here. Yes. So the question arises where this lone pair has to be placed here, whether it is to be placed in this equatorial position or, I mean, this equatorial position, this is axial, right? So, or apical also, this is also called as apical position or equatorial position. So, we know that in order to minimize, so these lone pairs will be placed in such a way so as to minimize the repulsion. So where will be the repulsion be minimum if it is placed at axial position or equatorial position? So there is one rule we can remember here. It is the Benz rule, which says that the repulsions will be minimum if the lone pair is present at the equatorial position. So if the lone pair is present at the equatorial position, the repulsions will be minimum. So that will be more stable. If there is a minimum repulsion, then that will be the most stable structure. Most stable structure. So it can be, I repeat once again, the lone pair here, it can be placed in the axial position or in the equatorial position, but it is placed in such a way that there is a minimum repulsion. If it is placed at the equatorial position, the repulsion will be minimum here. So the lone pair is placed at this equatorial position. So now let's speak about this logically, why the repulsion is minimum when the lone pair is placed at this equatorial position. So we know that if it is placed at the equatorial position, let's write it. So this is fluorine, these are axial, this is 1 and this is 1. Yeah, this is a lone pair. Now here in the equatorial position, right? So if the lone pair is placed at this equatorial position, we know that the lone pair bond pair repulsions will be more than bond pair repulsions, right? So if it is placed at eggshell position here, yeah, if the lone pair is placed at this, it is a minimum repulsion, because if the lone pair is placed at this eggshell position, it is at 90 degrees, right? If the 90 degrees, the repulsion is more. But when it is placed in this position, that is equatorial, it is 120 degrees. So the repulsion is minimum here. So as to minimize the repulsion, the lone pair is placed at the equatorial position. And so the structure now, when we come to a conclusion, the structure now, see, this is like something like this, right? Now when we tilt this, because of this repulsions, this is little, the angle is reduced here. So this is like seesaw, right? The person sitting here, person sitting here, and this is like seesaw. There is a fluorine here, there is a fluorine here, one fluorine here, and one fluorine here, right? So when we ignore this lone pair which is present here, so while taking the shape of this, I said we ignore this lone pair here. When we ignore this lone pair, so it looks like a seesaw, right? So this is the shape of the molecule. So the shape of the molecule is seesaw, and the geometry here is trigonal bipyramidal. Yes, bipyramidal. So this looks like a seesaw, right? This is slightly because of the presence of lone pair here, repulsions in between this lone pair and bond pair. So the angle is little reduced, and we see the angle here. It is in SF4. The angle is, yeah, let me check it out. 101.36, and there are two angles, and the other one is 86.33 in SF4. Okay, yeah, the shape is seesaw. Now when we come to this ClF3 here, so again this chlorine is seventh group element, so 17, so 2 8 7 7 valence electrons, so half into 7 plus number of atoms which is bonded to 3 and 5. So again trigonal bipyramidal, logically speaking. But we know that out of these five, three are involved in bonding, that is three bond pairs, and two other or lone pairs of electrons. And we know that according to the Benz rule, when these lone pairs are placed at the equatorial position, the molecule is stable, because there is a minimum repulsion when they are placed at the equatorial position. So the shape of the molecule, when we come here, when they are placed at the equatorial position here, so this is the shape of the molecule when they are placed at the equatorial position. This is a Cl here, and these are the lone pairs which are present, and one F here and one F in eggshell position, other F in the eggshell position. And now how does it look like? T, right? When we tilt this, T. So it is T-shaped molecule. The shape of it is T-shaped molecule, and the geometry is trigonal bipyramidal. Right. Okay, this is what is the structure of, I mean, the shape of ClF3, and the angle when we see this, it is 87.4 bond angle. Yes. This is what is ClF3. I hope this is clear. And now when we come to I3 minus, this is also according to the VSEPR rule. We can come to the conclusion here. This I is again 7 valence electrons, so half into 7 plus 3 is nothing but 5 again here. So 5 again, when we look at it, this is trigonal bipyramidal, right? So if it is 5, this is sp3d, which means that it is trigonal bipyramidal. I write it again, no problem. So just try to follow it, okay? Trigonal bipyramidal, and out of these 5 pairs, these are 3 are involved in the bonding and 2 other are, I'm sorry, 2 are involved in the bonding. The central atom is iodine here again. So 3 are lone pairs. How these lone pairs are placed in the equatorial position in order to minimize the repulsion. So these yellow ones are the lone pairs, and how does the shape of the molecule here? It's linear, simply linear here. So with the three lone pairs and 2 bond pairs, it is linear in shape. The shape of the molecule is linear here. Yes, this is what about I3 minus, and now coming to SF6. This sulfur again is 16, so we already know this to 8 and 6. So half into 6 plus 6. Okay, fine. This again 6. Oh, this is sp3d2. There's a new shape, now new geometry here, where the central atom is F and F. This is nothing but octahedral, right? So the shape is octahedral. The geometry of the molecule is octahedral here, and the shape is also octahedral since there are no lone pairs of electrons in this case. So when we do this, this is one plane of the molecule, and above and below the plane, there is 2 other fluorine atoms, and the bond angle in this case is simply 90 degrees, and there is no eggshell and equatorial bonds when we come to this octahedral shape here. So remember it. Yeah, we can talk about this equatorial and eggshell bonds only in the case of trigonal bipyramidal, and octahedral with a bond angle of 90 degrees. It is also called a square bipyramidal. See, this is square in shape and 2 pyramids above and below the plane. So it is also called a square bipyramidal. Right? Yeah. Right here. So this is square bipyramidal. So just to remember it, as soon as you look at the picture, you can come to the conclusion of the geometry of the molecule. It's as simple as that. Now, when we come to the example of BRF5 here, so this BR is again 7th group, so it is number of electrons is 7, half into 7 plus 5 is again half 6, right? So sp3d2. Okay, 1 2 1 2 3 4 5 6, right? So did I write sp3d2 here? Yeah, as simple as that. Yes. Now the shape, according to this, the geometry should be against octahedral, but we know that out of this 6, 5 are involved in bonding and 1 other is a lone pair. So this lone pair is placed in such a way that it will have the symmetry which is symmetrical here. So as the bond angle is 90 degrees here, so wherever you place the no problem, but now let's place it at this position because the molecule will be symmetrical if you place the lone pair at this position. Yes, and because of the repulsion in between this lone pair and bond pair, the angle here is, the shape of it, the geometry here is again octahedral. Geometry is octahedral, and we look at the shape of this because of sp3d2, with one lone pair, it is square pyramidal. Okay, one plane of the molecule and looking like a pyramid above this plane, right? Above the square, it's looking like a pyramid. So it is square pyramidal, and the angle is, because of the repulsion in between this lone pair and bond pair, it is 4.30. Yes. Then again, this IF7 here, I think this is the last example we are dealing with. I is again 7 here, so a half into 7 plus 7, this is 7. Oh my God, this is sp3d3. So one more will be coming into play here, where here it's connected to 7 other fluorines. So the shape of this, now this is tri 7, right? So if it is 7, we can say that pentagonal bipyramidal. Yes, the geometry of this will be pentagonal bipyramidal, because pentagonal in shape, and it's look like two pyramids above and below this pentagon here. This is a pentagon, one plane, and above and below the plane, it's look like a two pyramids. So looking at the picture, we can say that it is pentagonal bipyramidal in structure. This is a structure of IF7. So according to the VSEPR theory, now when we look at this chart, we can simply summarize this. So let me tell you, if the bond angle, geometry is linear and bond angle is 180, and its sp hybridization, if it is 120, it is trigonal planar, and the hybridization is sp2 here. And it is, in the case of, for example, if BF3, and if one lone pair is present, it is bent here. Okay, and if it is tetrahedral, if the geometry is 109.5, and it's sp3 hybridization, and as in the case of ammonia, if there is one lone pair present, it is trigonal pyramidal, and in the case of water molecule, two lone pairs are present, then it is bent here. And if it is the bond angles are 120 and 90, it is trigonal bipyramidal, sp3d, and seesaw arrangement. If one lone pair, if two lone pairs, it is T shape, and three lone pairs as it is linear, as in the case of I3 minus. And if it is 90 degrees with sp3 D2 hybridization, is octahedral, and if one lone pair is present, is square pyramidal, and if two lone pairs, square planar, and so on. Right. So this is a summary of what we have done, that is the VSEPR theory. And here, if we can see, it is steric number in this case is, it is, to summarize this, it is 2, here it is 3, it is 4, it is 5, and it is 6 here. With one lone pair, with 2, this is one lone pair, yes, this is 2 lone pairs. And here one lone pair, 2 lone pairs, and 3 lone pairs. Here one lone pair and 2 lone pairs, and so on. Okay, here it is one lone pair. Yes. One more thing I have to deal with. In the beginning of the video, I've said that the shape of the molecule is also decided. That means the bond angle by the electronegativity difference in between the central atom and the other atoms. So when we come to this ammonia and NF3 here, when we come to this ammonia and NF3 here, so when we look at this NH3 and NF3, that is ammonia and NF3, both here has the tetrahedral geometry. The steric number is 4 when you calculate here, with the presence of one lone pair on both of this. So they are pyramidal in shape, but the bond angles is different. Why this bond angles is different is, we can explain this based on the electronegativity difference here. We know that nitrogen is more electronegative than hydrogen here. So the bond pair of electrons here, when we see they are pulled more closer towards this nitrogen in the case of NH3. But F is more electronegative when compared to the nitrogen in this case. So the bond pair of electrons are pulled more closer towards this fluorine atom when compared to that of the nitrogen atom. These blue balls are fluorines. Okay. So because of this, they are pulling the electrons closer towards it. The the bond pair repulsions are reducing because uh, the F here is more electronegative. They're pulling the electrons more towards it. So the repulsion in between the bond pairs is less in NF3 when compared to that of this NH3. As a result of this less repulsions, the bond angle is reduced in this case. And the second reason is, in nitrogen here, as nitrogen is more electronegative than hydrogen. So that's the first reason. And the second reason is the lone pair in NF3 here, this lone pair is attracted more towards N here in NF3, because the bond pair of electrons are attracted more towards this fluorine. As a result, these are attracted more towards this nitrogen in NF3 when compared to that of the lone pair of electrons in nitrogen. As a result of this, the lone pair bond pair repulsions will also increase, and this will try to push further. This lone pair of electrons will try to push further this bond pair. As a result, this angle is reduced here. So because of these two reasons, the bond angle is less in the case of NF3 when compared to that of this ammonia. So the same thing I've dealt with this here. So more electronegative atom pulls electron density away from the central atom as in the case of NF3. So the region around this central atom becomes less crowded, and as a result the bond angle decreases. Yes. Now let's look at the limitations of this. Although it could explain the shapes and the angles so very clearly, it fails to explain the isoelectronic species. What are these isoelectronic species? These isoelectronic species are nothing but, the name itself shows, uh, the elements which are having the same number of electrons. So it fails to explain the shape of the molecules in the case of this isoelectronic species, although they have the same number of electrons in the valence shell, uh, but they differ in the shape. So it's unable to explain why they differ in the shape, and they does not explain the transition metal compounds also. So because of these failures, and new theory should be put forward, and the new theory is nothing but the valence bond theory, and I'm going to deal with this valence bond theory in my next video. So because of these limitations of this VSEPR theory, a new theory has been put forward, that is nothing but the valence bond theory.